Thank you everyone for coming out today to the undergraduate online mathematical physics seminar. Today we are very delighted to have our very own Shadi Tahvildar-Zadeh talking to us about one-dimensional hydrogenic ions with screened nuclear Coulomb field. So without further ado, why don't you take it away?
Thank you very much for the invitation. This is a joint work with two undergraduates here at Rutgers, Suchindram, Dasgupta, and Chirag, Khurana. They should really be giving this, but unfortunately they have classes at this time, so they couldn't be here. So that's why I'm doing it on their behalf. So what we're going to talk about is a situation where you have now let me see, how do I hide this Zoom thing?
I don't know what you want to hide. I mean, we can see you.
Well, you can't see it, but it's in front of my face, so I can't see my own slides.
Oh,
so that's what. Sorry. Let me briefly stop sharing. I think there's some technical issue here. Okay. And then, okay, now we start sharing again. These operations are not commutative. That's the point. So, okay, you can see my slides now, right? And now I'm going to make this into full screen. All right, that's better. Okay, so what I'm going to talk about is I'm going to imagine we have point particles in one-dimensional space, so points on a line, and one of the points is called the nucleus, and that one is fixed at the origin, and the other one is called an electron, and that one is free to be on either side of the origin, and its location, its motion is guided by something called a wave function. And we are only going to take into account electric interactions. This is because there is no magnetism in one dimension. So what the electron is going to feel is the electrostatic potential from the nucleus. And the goal is to find the energy states available to the electron. So let us briefly recall what happens in 3 dimensions. In 3 dimensions, we can study the same problem, and we find out that there is a lowest energy state available to the electron. It's called the ground state. And then there are a number of excited states, actually an infinite number of excited states. So these are the pictures that you have seen in your chemistry class. This is the Bohr model for the atom, where the nucleus at the center and the electron in circular orbits around it. And the idea of Bohr was that only certain orbits are allowed. And each orbit is associated with certain energy level. And then if the electron jumps from one level to the next, it will emit electromagnetic radiation. That's what these squiggly things are. And that's something that can be observed. Then Schrödinger wrote down the equation which gave rise to this spectrum. And using the equation, one can actually find the shape of the so-called electron probability clouds around the nucleus. And then they have these pretty shapes. And they are indexed by 3 integers. You can't see it here. This is too small, but this probably you remember. These are all these dumbbells and other beautiful shapes. And there's also something true about the energy levels that was discovered later on, that these energy levels that was predicted by Bohr and confirmed by Schrödinger are not the true ones. The actual ones, one has to, Schrödinger's equation being non-relativistic, one has to take relativistic effects into account. And when you do that, you find a correction to the energy levels. So for example, the n = 1 energy level is slightly less, and nickel 2 splits into two different states with a slightly different energy. And then Dirac wrote his equation, which was relativistic. It confirmed that this is the correct spectrum. Of course, today, this is not the full story either. There are further corrections, other effects, so which have to be studied in a different way. We are not getting into that today. So today, what we want to know is there something similar in one dimension? And well, if I'm giving this talk, you can probably guess that the answer is yes, but maybe more importantly, one has to say, why do we care about solving a problem in 1D if this problem is already solved in 3D? And the point is that this is just the beginning of the study of what happens inside an atom. This is already, there are several simplifications here. One is that we have fixed the nucleus at the origin. So that's an approximation called the Born-Oppenheimer approximation. The other approximation is that we have neglected gravity, for example. One can ask what happens if gravitational effects are included. So, and how would one go about that? Or we can ask, how does one model these squiggly things that are coming out here in this picture? These are supposedly photons. So how does one put photons in this story, and so on? So there are all these different directions that one could go, and conceivably in one dimension, some of these things are simpler. But as far as this question is concerned, the answer is yes, including some pretty pictures, not these, but similarly. And also, there are also some important differences that we will see between the 1D and 3D. One big difference you will see is that instead of infinitely many bound states, we are only going to get finitely many. So that's one remarkable difference between the 1D and the 3D picture. Okay, any questions?
Actually, only a minor comment that, of course, is tangential to the talk you are going to give. But in that picture of the hydrogen wave functions, I recently came across an article where somebody made the following point. See, these are all based on the separation of variables in spherical coordinates, right? Now, the Schrödinger equation for hydrogenic atoms is also separable in parabolic cylinder coordinates. And if you then plot the corresponding mod square orbitals, completely different pictures, right?
Yes.
So, and then a person raises the question, and why the hell should we choose those as representing what's going on? Why don't we choose the others, right? And I think this is actually a very interesting.
Actually, so, Michael, you're surprisingly, what you said is quite relevant to what I'm going to doing, because when you do that thing using parabolic coordinates, you get these special functions called Whittaker functions. Right. And the same Whittaker functions are going to make an appearance here. I see. And that's quite remarkable that they do. But actually, that's interesting. So, all right. So let's get on with this. So we write down Dirac's equation, which is this equation. We don't need to know much about what these things are. These gammas are certain matrices. The wave function for the electron is a two-component object in one dimension. It's two complex component. So it makes sense for this operator to be a 2x2 matrix. And the coupling to the electric field of the nucleus is through this term, where this phi makes an appearance. And this phi is the electrostatic potential generated by the nucleus. So if I remove that, that will be the free Dirac equation. And putting that in now says that we are looking at the interactions of the electron with the Coulomb field of the nucleus. So when you do that, you find out what this Hamiltonian looks like. It's going to be this 2x2 matrix. One thing to keep in mind is that even though this looks like a 2x2 matrix, and pretty soon we're going to be talking about eigenvalues and eigenvectors, this is not the usual notion, because as you notice inside, the entries of this matrix are not numbers, they are operators. For example, here is the d by ds. So this is an operator valued matrix. So, so one has to be slightly more careful about how to define the eigenvalues for this object. So this is something that you will see when you take a course in functional analysis, for example. So nevertheless, we can try to analyze this equation by looking for using separation of variables idea, looking for functions of t and s to be looking for a special functions where have just some periodic function in t, sine and cosines basically times a function of s alone. And this function of s alone will still have two complex components, which now we have to find out. So, so when we write down the corresponding equation that this little psi satisfies in its two components, we see that now this looks like an eigenvalue problem. So there's some operator acting on this vector is some number times the vector. And in this equation, both the vector R1, R2, and the eigenvalue are both unknown, of course. And the object is to find the values, real values E, for which this equation will hold for some functions R1 and R2. Now, R1 and R2 are, each one is complex. So it looks like we have 4 real degrees of freedom here, because each complex function is 2 real valued functions. But now we can use something called the gauge invariance of these equations to reduce the number of unknowns here. So it turns out that it is possible to reduce the number of unknowns to only 2 real unknowns instead of 2 complex unknowns. So this is called the reduced Hamiltonian equation. Now we have a slightly different matrix operator, right? That's acting on these 2 component real functions. And then we can write it like this. So now we are looking at the kernel of a certain operator, h minus e, and we want this operator, we want to find the values e, real values e, for which this has a non-trivial kernel in some, say, among the square integrable functions. So the unknowns, therefore, are u, v, and e. It's all unknown. So there is a general theory that goes with studying these type of equations, right? This, again, this looks like an eigenvalue problem, but one needs to be slightly more careful about it, because what's involved here are these differentiation operators also. So one can rewrite this reduced Hamiltonian in the following form. When you separate the differential part from the multiplication part. So, and then there are some general theory of this so-called one-dimensional Hamiltonians of this form due to a mathematician Weidmann, which tells you, first of all, under what conditions is this going to be self-adjoint? Why is that important? It's because we wanted this E to be real. So we are interested in real value. This E turns out to be the energy of the system. So we want it to be real valued, and for this operator to have real spectrum, it needs to be self-adjoint. So one needs to study under what conditions that is the case. And also next is, if it is self-adjoint, what is a spectrum? And the definition of a spectrum, as I was saying, is slightly more general than what you see in linear algebra. We said the operator h minus e, we're looking for values of e where h minus e does not have a bound with inverse. So now there will be 2 kinds of values of e. There will be discrete values. These correspond to the usual notion of eigenvalues. So there will be eigenfunctions associated with that, and those will be the bound states of the electron. And then there will be a continuous part, or the essential part of the spectrum, which correspond to scattering states or unbounded states of the electron. So that's and of course of physical interest are both of these things. You need to understand both of these. Now, if we do the same thing in 3 dimensions, as I said, the problem in 3 dimensions is very well understood. The Dirac operator has a certain essential spectrum, which is the real line, except for the interval from -m to m, where m is the mass of the electron. These are in units where the speed of light is equal to 1. And then there is a discrete part of the spectrum, namely the eigenvalues, which I showed you before. This is going to be a countable set, and it lies in that gap between -m to m. It's an increasing sequence, and it approaches this upper threshold m, actually. So that's the situation in 3D. And as we were going to see, the situation in 1D is somewhat similar, but it's not exactly this. So there will be some important differences. But now already in something in 1D, which is problematic, is that in 3 dimensions, the electrostatic potential from the nucleus is the usual Coulomb potential that everybody is familiar with, constant over mod x, and therefore it goes to 0 as the spatial variable goes to infinity. That's unfortunately not the case if you are in 1 dimension. If you solve the same Maxwell's equations in 1 dimension, you get that the potential is actually constant times absolute value of S, not 1 over absolute value of S. So this constant is Z, the number of protons in the nucleus, times the electric charge, from the unit of electric charge E. So that creates a problem already, because with this kind of potential, you cannot really expect any bound states for your Hamiltonian. And to apply Weizmann's result, one needs that multiplicative part to approach a diagonal matrix as S goes to infinity, and that requires phi to go to 0 at infinity. While if this is our phi, then it's not going to go to 0, and we have a problem. How do we fix that problem? Is we change our potential. So this is called the screening. Instead of the blue curve here, which is the absolute value curve the original Coulomb potential, we take the red curve, which corresponds to, first of all, moving this up a little bit, which is not a big deal. If you translate the potential, it's like translating the spectrum. But the important part is that you make it go to 0 at infinity, instead of it having this being unbounded. So now, why is such a thing justified? Well, if it is really true that the electron is going to spend most of its time close to the nucleus is where this singularity is, then maybe it's okay to change the potential far away, right? So that's one way to talk about it. Of course, this doesn't mean why do you have to take this specific one. It turns out that this specific one that we have chosen here there are other reasons that one can give why this is a good modification of the Coulomb potential. Be that as it may, we can pose the problem in this way, and then the study said this is the problem that we can study, so this is what we're going to do. Now, one thing that's interesting about these equations that we have to study is that this UV system that I showed you before, this eigenvalue problem, is actually a system of 2 linear ODEs, but coupled to each other. So the fact that the system is linear is very good. The fact that the 2 are coupled to each other, meaning that the V shows up in the U equation, that the U shows up in the V equation, is not so nice and makes it a little bit difficult to study this. So one way to get around that is to apply something called the Truffert transform, which is sort of the analog of polar coordinates, but on the other side, in the target side, right? So you define these 2 new unknowns, capital R and capital theta, in terms of the old unknowns u and v. So now you're working with capital R and capital theta as our unknowns. And when we do that, what happens is that the theta equation decouples from the R equation. So the theta equation is not going to have any R in it, and therefore we can think of it as an ODE. And moreover, we can do this standard trick which you do when you have a non-autonomous ODE, you can turn it in a cheap way into an autonomous ODE. So this is what I've done here, right? So now the unknowns here are capital theta, which remember was this, and S, which used to be the space variable. Now that's also the dependent unknown. And then there is this independent variable tau, right? So this is the ODE that we're going to be studying. And the point is that what about R, where R also solves its own equation? Theta, of course, shows up in the R equation, but imagine you can solve this and find what theta is. Then you can plug it in here and integrate this and find what R is. So this is what I have done here. So if you know theta, you can find R. And the condition we had on the UV system was that we were looking for the solutions had to be square integrable. So this UV have to be square integrable, which means that this capital R has to be square integrable. And when you look at what capital R is, you quickly realize that this exponential factor must go to 0 as S goes to infinity. Otherwise, capital R has no chance of being integrable, right? So that tells you about what sine of theta of S should be as S goes to infinity or minus infinity. And those are actually the boundary conditions for our equation. So we're going to study this ODE with this boundary condition that theta at infinity has to be negative and theta at minus infinity needs to be positive. So we are only interested in these solutions. So now the question is, what does that mean geometrically, right? We can convert the theta equation into a flow on a compact cylinder. We can do that by another change of variable when we go from the S, which went from minus infinity to infinity, to the Z variable, which is arctangent of that. So now that just goes from minus pi over 2 to pi over 2. So if we now compute what the derivative of Z is, we get this new dynamical system now. And now the variable Z goes from on an interval, and the variable theta goes on a circle because it's an angle. So this is a dynamical system on a cylinder. So it's very important to keep in mind that E is still unknown. So this dynamical system depends on two parameters. One is this E, which we don't know what it is. And the other one is this gamma, which is basically the number of protons in the nucleus, right? So now the object becomes, are there E values for which this dynamical system has a solution theta Z, where theta satisfies the boundary condition that we want, right? Any questions? Okay, good. So, well, how do you study a dynamical system? You first find out its equilibrium points. So we set the right-hand side here equal to 0. Where is cosine of Z 0? And where is this thing 0, right? So when you do that, you see that there are going to be equilibrium points when these equations are satisfied. So now this is going to depend on E because E is an unknown, right? I'm taking its arc cosine. So if absolute value of E is bigger than 1, there are no such things. And when it's less than 1, there will be 4 equilibrium points. And when there is equal to 1, you'll just get 2. So when absolute value of E is less than 1, you get 4 equilibrium points. Notice that these are modulo 2 pi because theta is an angle, right? So you can add 2 pi to these and won't change anything. And when E is equal to 1, you only get 2. And V is equal to minus 1, you only get 2. Now notice something very important. all of these equilibrium points are on the boundary of the cylinder. So imagine a cylinder like that, horizontal, right? It has a left boundary and a right boundary, and the equilibrium points are always on the boundary of the cylinder, right? 2 on the left and 2 on the right. If you are energy less than 1 in absolute value, and 1 on the left and 1 on the right, right? If energy is equal to 1. And also here, plus and minus pi are the same point. So that still counts as 1 here and 1 there. Okay, so this is the picture that we have now. And now what do you do next? After you find the equilibrium points, then you need to do a linear analysis to understand what the flow looks like near each equilibrium point. And there's a standard theorem that you learn in ODEs, is that the behavior of the flow near the equilibrium point is controlled by the eigenvalues and eigenvectors of the linearized system. When you take the right-hand side and you linearize it, right? So you have the matrix of partial derivatives of the vector field, and the eigenvalues and eigenvectors of that dictate the flow. When you learn this in first ODE course, they tell you that this is only true. You can only make this comparison if the real part of the eigenvalues is not 0. So the theorem that you typically see is that if the real part of the eigenvalues are not 0, then what I'm saying here is true. Then the nonlinear flow is controlled by the linear flow. However, all bets are off if the real parts of the eigenvalues is 0, right? Well, that's not quite true. There's something more sophisticated called center manifold theory, which applies precisely to the case where the real part of the eigenvalues are 0. Then you have to work harder, and the theorems are not as simple to state in that case. And unfortunately, in our case, that is going to be the thing that we have to deal with. The real parts, actually, forget about the real parts. The eigenvalues, one of them is always 0 for us. So we always have to be in this context. But fortunately, there is still a corresponding theory called center manifold theory, which still says that you can, under certain conditions, do this thing. So we do that, and it emerges that we have 2 different behaviors at each end, right? So remember, there are 2 equilibrium points on the left and 2 equilibrium points on the right, right? The 2 on the left, near one of them, you see a saddle behavior, right? And near the other one, you see a node behavior or a source, which we used to call it in ODEs, right? So you have a saddle behavior, type behavior, and a source type behavior on one side. And on the other side, you again have a saddle type behavior and a source type behavior. A sink behavior on the other side. So things on the cylinder, on this cylinder, they're always going from left to right. And so things are going to start here and they're going to end here. And now you can see if you are at S minus, there is a unique orbit that's coming out of S minus. While if you are at N minus, there is no unique orbit that's coming out. Everything is coming out. Similarly, when you are at S plus, there is a unique orbit that runs straight into S plus, while if you at N plus, there is no unique orbit. Everything is sucked in to N plus. In other words, the center manifold is unique only for S minus and S plus. The center manifold is this thing, this unique orbit, right? So now remember we had these boundary conditions, right? We were only interested in certain type of solutions of this dynamical system. So when we look at that, right, it turns out that we need solutions that come out of this S minus and run into this S plus. Those are the ones that we need. We don't want the other ones. And of course, if magnitude, this whole thing is under the assumption absolute value of E less than 1. If absolute value of E is equal to 1, the system is too degenerate, meaning both eigenvalues are 0 now. So even the center manifold theory doesn't apply. But we get lucky, as one hopefully gets, and it turns out that in that case, the equations are exactly solvable. So when I was telling Michael that his comment about parabolic coordinates is not so far off, in this case where absolute value of E is equal to 1, the ODEs are exactly solvable, and the solutions are something called Coulomb wave functions or Whittaker functions. They go by different names. And that's actually turns out to be very important for the analysis that we want to do. Okay, so to summarize, we want theta to be negative at this end and positive at this end. This means that we want things to come out of this saddle point and go into that saddle point. So we are only interested in saddle connectors, right? An orbit of a dynamical system that starts from one equilibrium point and ends at another equilibrium point, it is called a heteroclinic orbit. So,
please interrupt, Shadi. Did you choose this particular regularization so that you can solve the case E equals 1 exactly, or was that accidental?
No, that was just pure luck.
Pure luck. Okay.
I can tell you how we chose our potential. So if you think of the Coulomb potential, right, it's a fundamental solution of the Laplacian, right? So we just took the fundamental solution to Laplacian plus 1. Sorry, Laplacian minus 1.
Okay.
So you get this exponential. In other words, to put it in a different way, our photons have mass. That will give you this thing. So that's, but it was pure luck then, I think, that we still got Whittaker functions to come out. But only in this case, only in this threshold eigenvalue.
Yeah, sure. But still, the threshold is, of course, a degenerate case where the rest of the method fails. So in this sense, it's just put the doctor on. Okay,
yeah,
good.
in fact, this is quite different from the situation that we worked on together with ZGKN, because there at the threshold you do not get any orbit. There is nothing connects the eigenvalue, nothing connects the equilibrium points at that point, and that's why I think that's the reason why there we got infinitely many eigenvalues, and here you are going to get only finitely many, because these things, when they exist, they become a barrier that will stop things from falling even further down. So this will become clear later on. So right now, yes. Okay, so of course, I am showing here only the picture between this equilibrium point and this, but remember that in this direction we have a circle. So if you unwrap the circle, this will be a whole strip. And this thing, when it falls down, it can go to a different copy of this thing. So orbits can wrap around the cylinder, in other words, as they go from left to right. The number of time an orbit wraps around the cylinder is called the winding number of that orbit. And different winding numbers for orbits connecting S minus to S plus are going to correspond to different energy states. So that's the kind of the integer that we get here, is this winding number. Now, as I said, it may be useful to unwrap the cylinder into a strip, in which case an orbit winding number n will drop by 2 pi n as it goes from the left boundary to the right one. So that's how you can see how the winding number comes into this picture. Okay, so this is a diagram of that. So now we have the cylinder. Here you see an orbit with winding number 0. And here you see an orbit, the green one has winding number 1, right? Because it's going around once and doing that. And the object of for us is to, can we prove, the question to ask is, can we prove that for any given winding number n, you're going to get a saddle-saddle connector. Can one prove that? And you will see what the answer is in a second. So how would we prove the existence of eigenfunctions for various Poynting numbers? There's a general method, which is if you want a certain orbit for your dynamical system to go somewhere, you create barriers around it, right? So you find out curves in your space where your solution cannot cross one way or the other. So, and the point is, if you put a barrier above it, then it would have to go below something. And if you put a barrier below it, it cannot go further below. It has to stay above it. And this way you construct, if you can prove these barriers, then you can maybe construct the kind of solution that you're looking for. So there's a general procedure for that is described in this proposition, which uses Green's theorem. So imagine that you have two orbits, one with corresponding to different energy values. So it turns out that if you increase the energy, it forces the orbits to go down more. So energy shows up with a negative sign in the front. So higher energy means it's higher winding number. So if you find two energy values where the winding number corresponding to the bigger one is greater or equal to n plus 1, and the winding number for the smaller one is less than or equal to n, then you can use basically intermediate value theorem to show that there's the kind of solution you want in between, with the energy in between, and with the winding number that you want. So let me briefly describe that pictorially. This is the situation where you have lower energy. So it is coming out of S minus here, and you want something that will go to S plus, but that's not going to happen. Most of the time it will go to N plus, because remember, that's an attractor, right? And similarly, if you run this one backwards, it will probably go to N minus or some copy of N minus. So suppose you are in this situation, well, you will start here and you go there. And if you run this backwards, you go here. So now you have this shape with, you have this area enclosed, right? And if you orient this area, you can orient the boundary, then you can use Green's theorem to compute the area, the signed area of the inside. And you can see easily that the signed area of this one will be negative. Now imagine you turn the crank up, you increase the energy. So now the thing that's coming out of here, instead of going to this one, because you pushed it further, it goes down to a copy of that one, right? So now this is the situation with higher energy. And similarly, the one that starts back here, run it backwards, will go to higher one than before. So now the orientation of this shape has changed. This was negatively oriented. Now this becomes positively oriented. So the area of this region, the signed area, will be positive from Green's theorem. And now, so the area here is negative for this energy value, and here it's positive for this energy value. Area is continuous function of the energy. You use the intermediate value theorem that you learned in Calculus 1 to conclude that there is some energy value in between where the area is 0. Well, if the area is 0, how can the area be 0? It means that this thing must collapse, and that would be the solution that you want. That you will find some solution that starts at S minus and goes to S plus. So that's basically the proof of how to get a solution if you can construct this low energy and high energy barriers. If you can do that, then you're done. So then the problem becomes constructing this and because higher energy means you get a low barrier, the highest possible energy is equal to 1. So if you have a solution for E equal to 1, that's the mother of all floors for your dynamical system. And if you can orbit with E equals -1, would be the mother of all ceilings. it will be a universal barrier for all functions, right? And these are the ones that we can solve explicitly, the equation. So we know that they exist. All right, so and this is what now, this is about E equal 1. When E equals 1, there exists a sequence of values. We prove this. For gamma, remember gamma is the nuclear charge, right? If gamma is between two consecutive values, gamma k minus 1 and gamma k, then there is a heteroclinic orbit with winding number k, and another one with winding number k plus 1. So for E equal 1, you get actually two barriers with different winding numbers, right? And this, the proof of this theorem involves studying that particular ODE when you set E equal to 1, which I said is exactly solvable. So first of all, we note that theta is, you recall theta was this, right? So U is in the denominator. Suppose U is 0 somewhere. If U is 0 somewhere, arctangent of infinity is going to be pi over 2. So this becomes pi. So we will transition into a different branch of arctangent if we go through a 0 of U. So every time we go through a 0 of U, we go into a different branch of arctangent. So what does that mean? On the other hand, if you increase gamma, d theta ds becomes more negative. So it's forcing the solution orbit to wrap around the cylinder even more. So each time U is 0, theta is pushed down into a lower fundamental domain. So the takeaway is the number of zeros of U dictates the winding number, right? So what is this sequence of gammas that dictate the available winding numbers? It turns out, and here's the magic that I was promising, right? Here's the miracle. When you set R equals to gamma e to the s, V as a function of R now, remember V was a function of this S. But if you do this change of variable, V as a function of R satisfies a special form of Whittaker's differential equation, which is this one. Okay, so V satisfies this equation. And this equation has two linearly independent solutions. These are called Whittaker functions. There's a Whittaker M function and there's a Whittaker W function. They usually have two parameters. We have to choose these particular parameters here. And also notice that the argument of them is imaginary, right? So the other name for Whittaker functions with imaginary argument is Coulomb wave functions. That's another name for them. So, so V being a solution of this ODE will be a linear combination of these two. This is a standard ODE. Then there's a standard ODE result called the Sturm separation theorem, which says that the zeros and critical points of the Whittaker M function will control the positions of the zeros and critical points of V. Right? So now we need to look at the zeros and critical points of this particular Whittaker M function. These you can compute. These are examples. These we have computed the first four here, right? So the odd ones are roots of the derivative, and the even ones are roots of the function itself. And both are important for our analysis. Okay, so you get these critical gamma values, which means that as you go, so now it really, the role of this parameter gamma becomes clearer. If you put more and more protons in the nucleus, if you increase the charge of the nucleus, you're going to be crossing this threshold at some point. And as you do that, the winding numbers of the solutions will change because it depends on that, right? So now you can also see that U, remember we wanted zeros of U. Zeros of U control the winding numbers. Zeros of U are the same as, turns out they're the same as critical points of V. So, so here's the picture of this. The black thing is the Whittaker function, the one that controls everything. The blue curves are the graphs of V as a function of R, right? We have chosen a particular gamma, which is equal to 7, happens to be, right? So it's somewhere here. You see, this is the less than this 0 of the Whittaker function is here. And if you choose this particular gamma, there will be 2 particular solutions for V equation. And let's count the number of critical points. This one has 1 critical point here and 1 here. So it has 2 critical points, right? Now I need to reflect that with respect to this end. So if I reflect that with respect to this end, I will get 4 critical points for V. That will be 4 roots for U, right? So that will give you a winding number 4. So the dotted thing is going to have a winding number 4. And when you look at the solid one, let's count the equilibrium, the critical points here. There's 1 here in the beginning, close to the beginning. There's 1 here, and there's 1 at the very end. So this is now 3 critical points. Now you need to reflect it with respect to this end. So at this end, you're not getting an extra 1. So now this is going to have 5 critical points. So U is going to have 5 zeros. So the winding number of this one is 5. So that's kind of the proof of that theorem. And now a consequence of that is that you will get, you will know what the winding number of actual solutions are. Oh, by the way, the same thing is true for E equals -1. The different Whittaker function shows up with different zeros and critical points and so on. But otherwise, it's exactly the same. Here's the main theorem. Given any J and K, if gamma is in the intersection of these 2 intervals, then you will get a saddle connectors with winding number n for every integer capital N lying between J and K, right? So that gives you a full description of how many bound states you're getting and what is their winding number. And as you can see, it's a finite number. And it does depend on where this gamma is, right? That's the parameter in the problem. We're going to see a picture of that very soon. So here are some, let me use the remaining time to discuss about some numerical investigations that we have done. Ideally, you want to actually compute these energies, right? So recall this was our ODE before we messed with it to turn it into a dynamical system. That's what the original ODE was, right? So we can ask, what is the relationship between gamma and the corresponding bound state energy level E, right? And how does this relationship change for different winding numbers? So this is the picture that we get. In the horizontal axis is the gamma value that you choose. The vertical axis are the energies of the bound states that come out of this theorem. And the colors represent different winding numbers. So now you can see how it works. If you choose a gamma value here and go up, it's going to intersect these curves. It's going to intersect finitely many of these curves at some points. And those will be the corresponding bound states, right? In particular, notice that these curves do not start here at 0. So if you take a very small value of gamma, there will be only the ground state. And if you increase gamma, then there will be 2, sometimes there will be 3, sometimes there will be 4. It fluctuates because of that, because this is what you need to do. So we have not finished completely studying this fluctuation. That involves studying the zeros and critical points of these Whittaker functions that are involved. But that would be an interesting study on its own that one can do. Okay, so So this picture is somewhat reminiscent of the picture that you get for the standard hydrogen problem, but again with some fundamental differences. In particular, that there's only finitely many of them that you see. So these curves don't all go all the way in to here. They really start somewhere. Okay, so one can also use this characterization that we have. It turns out that this is very useful to find the energy values using a binary search. So, and when you do that, you just have to remember what this R and theta were in terms of U and V. And now one can also see how does the picture look like if you have a solution in theta that gives you a solution in R. And if you have theta and R, that gives you a solution in U and V. So now you get U and V as functions of S. Now you can view them as a parametric plot. So you can plot these solutions in the UV plane and see what kind of curves you're getting. So clearly, they would have to start at the origin, because as S goes to minus infinity, right? You want U and V to be 0. And also when S goes to infinity, you want U and V to be 0. This is because R is going to be 0, both at infinity and minus infinity. So these are going to be curves in the UV plane that they start at the origin and they end at the origin. But then they do something in the plane. How it's interesting to see what is it that they do. What kind of curve do we get? And is there possibly a connection between that and this winding number that we had defined? So here's the picture. This is the ground state now. This is how you will compute the energy by the binary search. So you're looking for some unstable solution, right? So you keep changing the energy, and either you overshoot or you undershoot. But if you make the window smaller and smaller, you will be able to find finally the unstable solution sandwiched in between. And that's what the theta solution looks like. Can you find it? So this is the corresponding R. This is nice and decaying exponentially at the end. And this is the picture in the UV plane. You get this kind of curve. It starts at the origin, it goes around, and it comes back to the origin. Okay. Now, what happens for the first excited state, right? Can you guess what the first excited state would look like in this picture?
Well, one loop extra, right?
Well, not quite, but yeah, I mean, you have the right idea. It should something that should be going around more, right?
Right.
But remember, it has to stay at the origin, start at the origin and end at the origin.
Yeah,
right?
yeah, sure. But in between, it may loop once around extra. So
yeah, and also it has to have the same tangents as this one. It turns out.
Yeah,
but have to start right. So okay, so here's what it is. Ta-da! Right. So you can send this to your best friend on Valentine's Day and say, I am so excited about you. Because that is the excited state. That's the first excited state. So now you see that theta is tumbling down more. This is the interesting, the probability. Remember, this is the probability density, right? The probability density develops a peak on each side. So that's, and this is the picture in the UV plane, right? And you can go more, say winding number 2, right? Theta is tumbling down even more.
That's actually the picture that I had in mind. So you go
this one,
to the right side and then you loop around, even though I thought the loop would be smaller. Now it's bigger.
Yeah, but so nicely like this, and then like that. Yeah, that's so that's finding number 2, and that starts to look like Batman or something here, and then and this is finding number 3. That's again more peaks. You can see the pattern, right? And more looping is this like this and goes like that and then comes back around like that. So that's all right. So to summarize, we proved that the Dirac Hamiltonian for a single electron in a screened nuclear Coulomb field is essentially self-adjoint, has the usual essential spectrum, and has a finite number of eigenvalues in the gap. We identified the energy eigenfunctions with heteroclinic saddle connectors of a certain dynamical system on a finite cylinder. We showed that the number of bound states and their energies is determined by the nuclear charge. This identification allowed us to effectively compute the energy levels and the shapes of the orbitals. Here are 2 future directions to go. What happens if we quote unquote turn on gravity? And we kind of know that it will be nothing good, because in 3 dimensions, when you try to do this in 3 dimensions, all hell breaks loose, and you basically lose everything. But maybe in 1D, the situation is different. So this is something that we would like to study. Another possibility is, okay, now you have these excited states and ground state and so on. Can you put a photon in the story and study the emission absorption phenomena in this 1D context? Okay. And there are other things that conceivably one can do, which I did not have time to mention. So thank you very much for listening.
Okay, let's all unmute ourselves and give our speaker a round of applause. Thank you very much.
Yeah, very good work for these undergraduates that you work with. I don't remember the names precisely, but
yeah, Suchindram and Chirag. Yeah, indeed, they worked very hard on this, and they've been working for about 2 years on this problem. It's starting from them not knowing anything and learning about quantum mechanics and differential equations and functional analysis and dynamical systems and all of these things, and then getting to this stage where they were able to pull this off. That's
yeah, not bad, not bad. Do you want to send it to Involve again?
Yeah, we are writing the paper up, and we're going to send it to Involve. That's
not bad, not bad.
I want to open the floor to any questions that people might have.
Well, I already took the floor, so maybe somebody.
Yeah, I do have a question specifically about the E=1.
Right.
So do you think that if you had chosen a different screening, so in the screening you have a choice about what mu to take.
Yes.
In your case, you took mu=1.
Yes.
So if you had chosen a different screening, chosen a different mu, then do you think that this would change the instead of E=1 plus minus 1, it would be plus minus mu instead as your ceilings?
So the 1.
Actually, I think it would be 1 over mu. I think it would be 1 over mu. That would be your ceilings.
Oh, I'm not sure. I mean, it's a good question. We should have done that, right? We should have seen what the effect of this screening parameter is. That's but yeah, I think I don't know how it affects it. It's some kind of a scaling, clearly. So you can imagine that you have chosen a length scale now, which I don't think we have done so far. Because we had said we are working in units where C is equal to 1, and H bar is also equal to 1. So we have one more unit to pick. before everything is fixed, right? So we could choose, I guess, we can say that we have chosen mu to be 1.
Yeah.
Right? But if we do it that way, then this should not affect what you were saying. But no, actually, okay, yeah. M will still be there. Okay, no, so I take it back. We did take 3 things because we also said m equals to 1.
N equals to 1?
The mass of
M,
the
yeah,
electron.
yeah.
So when we say that E equals 1, it's not really 1, it's m. Right? It's not really 1, it's m there. Because the energy, the threshold eigenvalues or the threshold points, right, are mc squared and minus mc squared, because they have to be like energies, right? So strictly speaking, we should not be allowed to set both m equal to 1 and mu equal to 1, because that would be too many now, right? So my guess is that if we only set mu equal to 1, then m will stick around. And E will still be, the interval will still be minus m to m. Right?
Yeah, and so, this is a good picture to have in mind, because my thought process is that, therefore, I think the mu will kind of change a lot of your answers then, depending on the mu.
You could say, here's, I think what will happen is that you are now measuring the mass of the electron in units where this screening length is 1. Right?
Yeah.
And what is that? Right? So that's right. So now you have a parameter. Now this mass becomes a parameter.
Yeah.
And then you would have to see how things depend on it. So yeah, I guess that is actually something that we could have looked at, or we could in future look at. Somebody could in future look at it.
And so something regarding the dynamical system that I wanted to ask is, I understand why we take U and V, why we take R to be 0 as S goes to infinity, but why do we also take that as for S equals 0?
For S equals 0, no, it's S. S is the space variable.
Yeah.
S equals 0 is where the nucleus is.
Yeah.
Right? We are looking for solutions that are square integrable. So U and V should be square integrable.
Oh, and so you were saying at positive infinity and negative infinity, that was the 2 points.
That's the only 2 points, right? At the origin, we don't have anything, right? Yeah, the origin is not a singularity here. Well, it is a kink for the potential, and it does contribute to something, right? But it doesn't, it's a regular point for the ODE. Let's put it this way. It's not a singular point for the ODE. Unlike the 3-dimensional case. So you could say that this is also another way that the 3-dimensional case is different. In 3-dimensional case, the radial variable only goes from 0 to infinity. And there's a singular point at 0. Right? So it's a different picture. So that's interesting that even though the pictures are very different, the same differential equation shows up, which is this thing that Michael was saying. That's right. Some transformation involving logarithms and so on that's is involved here.
So I guess something I want to ask is how should we be thinking about these bound states? Because, in an orthodox quantum mechanics class, in undergraduate class, you'll learn about the 3D case, and you're kind of told to interpret the orbits as like, well, classically, you think about the Bohr model and the shells and that sort of
Right, yeah, right, yeah.
So is there a similar interpretation happening here?
Well, clearly not. And even that three-dimensional interpretation, as we know, is incorrect.
Mm-hmm.
The planetary model for the atom is the wrong thing to think about, because if the electron is truly going around the nucleus, it's going to lose energy.
Yeah.
Right? So in fact, what happens, according to Bohmian mechanics, is that it will just sit there, staring at you. And that you can see, even in this model, you can compute the Bohmian velocity of the electron, and it will be zero always.
Really?
In the bound state, the electron is not going anywhere. It's just sitting there. Why is that strange? That's not strange, because the law of motion is not a Newtonian law of motion. It's a quantum law of motion.
Yeah. But isn't it, shouldn't it kind of depend on like modulus of one wave function component minus
and the two components have the same modulus.
Oh, okay. Mm-hmm.
Exactly.
Mm-hmm.
This R thing that shows up is the modulus of one component, which happens to be equal to the modulus of the other component. So then the velocity is zero.
So it's bound.
It's literally a steady state.
Mm-hmm.
Right. Well, interesting. Maybe that's an interesting angle to this, to study the stability of these.
Yeah, that was my first thought. Was
right. That's
how stable is that motion?
So I think that's an interesting problem. That's actually something that I suggested to some undergraduates to work on, to see whether that can be worked out, and whether there's a connection between the stability of these and the emission absorption. All right, I think we are lunchtime.